Oh, that's correct.
Trust me, I learned the hard way.
All right, folks, we're going to go through the kinetic molecular theory, gas laws, and ideal gases practice. And in your notebook, this is on page 73. As we go through this, I got some people in the classroom, and they may ask some questions. And if we get to a question that requires us to know something from another place in the notebook, we'll turn to that place in the notebook. So here we go. Let's start with this first one. This is about understanding kinetic molecular theory. And to understand this, you're going to need to take a look at PV equals nRT. And this is in your notebook. What page is this on? There it is.
66.
All right, so this is on page 66 if you need to go turn there. All right, so what we're going to do is go through and think about the relationships between these variables as we walk through this question. So first, the amount of gas in a sealed container decreases. And actually, the word here should be rigid. We're recording. Have a seat. You're good. This is a rigid container. You're okay. Have a seat. No, it's we're just recording the screen. Great. I'm not concerned. I'll be here second half today. Okay, great. For all my people watching, that was Schaefer and... No, I'm just kidding. All right. So the container is rigid. What does this mean for our ideal gas laws? What does a rigid container control? Yeah, certain volume. All right, if the container is rigid, that means the volume can't change. This also says that the temperature of the container stays the same. So we know that if we're looking at PV equals nRT, the volume is not going to change and the temperature is not going to change. Now over here, they say the amount of gas decreases. Which of these variables is the amount of gas? N, that's right. So if this side, N decreases, what's going to happen on this side? Pressure will also decrease. Okay? So that's our effect. So let's go through these one at a time and see how you do. We'll do PV equals nRT again. And please ask me questions if I say something and you're like, I don't get that. I thought it would be the opposite. So the pressure of gas in a sealed container decreases. If it's sealed, which one of these is it controlling?
Volume.
Not volume. That would be rigid. If it says it's rigid or inflexible, or if we know it can't.
Pressure.
Not pressure. Because pressure can still go up or down in a sealed container.
Is it the amount?
The amount of gas. Because it's sealed, no gas can enter or leave. Very nice. This also tells us that the volume does not change. All right, well, so we're left with two variables. Remember, this R never counts as a variable. It's a constant. It's always just a number. Okay. So, if the pressure of the gas in the container decreases, what's going to happen to the temperature?
It's going to decrease.
Right, the temperature is going to decrease. Whatever happens to one side of the equation has to happen to the other. So there's our effect. The temperature decreases. If you need me to help you with those chips, you just let me know, all right? I'm here for you.
She had some earlier, but
I had about 100 earlier, average. Wow, what a day! All right, so ladies and gentlemen, these chips and salsa are going to be in the thing now. You can still learn, right? Okay, here we go. Wow, what a day. All right, next one. The temperature of a gas in a sealed container decreases. So PV equals nRT. Who wants to walk me through this problem? Who wants to walk me through this problem?
I can try.
All right, go ahead.
Because it's sealed in the container,
Mm-hmm.
then it can't, the amount of substance can't change.
Right.
Neither can the volume.
We're not sure about that one.
Okay.
Okay? Remember, a balloon is technically a sealed container. It's not what we think of when we think of a container, but it is.
Okay.
What do they say we can assume here?
The pressure will not change.
Right, they also say the pressure will not change. So let's think about this. If the temperature decreases, what's going to happen over here? The volume's going to decrease. Very nice. A good example of this is what happens when you put a balloon in the fridge. If you've never done that, it's just one of the joys of having balloons sitting around. So blow up a balloon, tie it up, and then put it in the fridge, come back and see it in an hour. The poor guy will look like a little raisin. It's adorable. All right, on this last one, we're going to work backward. So let's think about this. Go ahead.
Does that also work for humans?
No, the humans don't get smaller, they get deader. So we don't do that, yeah.
Okay.
Okay, PV equals, and for anybody watching the recording, I swear I was asked that question. I didn't just say that out of nowhere. All right, so our effect is that the volume of the container increases. Based on the assumptions, what's not going to change? Well, it says the temperature and the pressure don't change. Pressure doesn't change, temperature. So what's left? What must have been the cause? The amount of a gas. You tell me, did it increase or decrease?
Increase.
Increase. It's like we're blowing up a balloon. All right, my dears, before we move on, any questions about this? No? Wow. I was really hoping you would ask a question so I would have a second to eat a chip. Okay, here we go. So second question, and this is connecting back to our our engines. If a combustion chamber experiences a rise in temperature, what will happen to the pressure in the chamber? We're going to assume the piston does not move and the exhaust valves do not open. So this is what they're telling us. When they say the piston does not move, they're telling us the volume won't change. Here's how you know that. If we take a look in our notebooks on page 62, this is the piston. Whoop. This is the piston. It moves up and makes the volume of the combustion chamber smaller, or it moves down and makes the volume of the combustion chamber bigger. It's a little bit like a syringe, if you've ever seen a syringe. So the volume is going to be constant. It also tells us that the exhaust valves do not open. What does that tell us?
It's a sealed container.
Right, it's sealed. That means the amount of gas is also constant. All right, so now we're asking what will happen to the pressure in the container. Well, PV equals nRT again. The volume's constant. The amount of gas is constant. R is always a constant. It says it experiences a rise in temperature. So what's going to happen to the pressure?
It will increase.
Yeah, it will also rise. It's not like a seesaw. It's like if this goes up, this has to go up too to stay equal.
That's exactly why I wrote. I don't know why I put my thumb down.
No, you're good.
I literally wrote the
Pressure.
pressure will rise.
So you can say rise, you can say increase, any of those are fine. All right, any questions on that before we move on? No? All right, the next one is where we get into thinking a little bit more deeply about this. So how can we increase the volume of a compression chamber, moving the piston and driving the motor? Assume that the exhaust valves do not open. What do you think?
By increasing the temperature.
Okay, tell me more. Talk me through it.
I said because when you increase the temperature, the volume also increases.
Okay, we increase the temperature, and that means the volume increases. And that would increase the volume of the compression chamber. Why? How do we get from the idea of increase in temperature to increase in volume? Can you talk me through what's going on with the molecules?
They start to move around more and end up pressing against the side of the chamber.
That's right, they move faster, they press against, it's actually called the cylinder head, but yeah, the top of the chamber. Okay, they move faster, they press across the top of the chamber, press against the top of the chamber. That's a higher pressure that we're seeing. All right, so it's an increase in pressure. All right, and as they press against the top of the chamber, they also press against what?
The side.
The sides and the piston. Don't forget, if these gases are moving faster, they're bouncing around in here. Yeah, they're hitting the top of the chamber harder. They're also hitting the sides harder. They're also hitting the bottom harder. And when they hit that harder, that pressure literally pushes the piston downward. And when that piston gets pushed downward, it turns this arm. This arm is called the drive shaft. It turns this, which turns the wheels in your car. All right. So my gentleman that just joined, we are working through the questions on page 73. Okay. Yeah, here for you. All right. So it also pushes on the piston. Moving it down. And by moving the piston down, it increases the volume in the compression chamber. Nice work. All right. Anybody have questions for me on that one? None at all. I really need someone to ask a question so I can eat a chip while you ask a question. All right.
Why is the sky blue?
Great question. Now, let's talk about gases. All right, so here we go. Here's why I like PV equals nRT. You're not going to need it for every question, but it's a great way to figure out which variables you're working with, especially in a problem where it tells you about lots of variables, but only some of them are changing. So, PV equals nRT. Which one of these can we cross out right off the bat? R. Why? It's always right. It's always constant. It's never going to change. It's a constant. It's literally its job is to never change. Okay.
What's R again?
R. Oh, good question. So the reason everybody told you to be quiet when you walked in is we're recording, but please ask questions because then I can explain them to anybody watching the recording later. So that's perfect. So if you turn to page 68 or 66, excuse me, you will see all of these explained. P is pressure, V is volume, N is amount of substance. R is a gas constant. It's literally a number that's inserted so that the math works. Okay? Because there's nothing, mankind made up these measurements, these measurements, these measurements, these measurements. We made all these. So to make the math work, we have to insert a number that kind of accounts for the differences between all these. So 0.082 is the R value for if we're using atmospheres. 8.314 is the R value if we're using kilopascals. Okay? Great question. So that's why R never changes. So we're recording this, that's why they're giving you the quiet. All right, here we go. If a gas has a pressure of 84 kilopascals and a temperature of 35 degrees Celsius and is heated to an additional 230 degrees C, what will the new pressure be? Assume the volume of the container is constant. So we're going to cross this out. All right. If it's in a container, they already told us the pressure is changing, and they told us the temperature is changing. It says container. It doesn't say a sealed container, but I think since it didn't give us any change in the amount of substance, I think we're safe to assume that that is also not changing. All right. All right. If all you have is pressure and temperature, which gas law are you going to work with? Well, let's take a look at page 67. Which one of these laws helps us with pressure and temperature? Guy-Lussac's law, that's right. Pressure over temperature equals pressure over temperature. So here we go. Let's set this up. The initial pressure over the initial temperature is going to be equal to the later pressure over the later temperature. Now, we have a problem here. Has anybody noticed? Kilopascals we're fine with. That's great.
It's not in Kelvin.
That's right. It's not in Kelvin. We have one no-budge rule about temperatures when it comes to gas laws. Always Kelvin. All right, so 35 degrees Celsius. Let's convert this to Kelvin. How do we convert from Celsius to Kelvin?
277.
That's right. We're going to add 273.15, and that will give us degrees Kelvin. Anybody got a calculator handy? Did I clean them all up? Oh gosh, I cleaned them all up. All right. You have it right here. I know, but I want my people in the recording to get to see the typing. I think it's not about the typing. It's more mother. There we go. It's more about like having the time to type it yourself when you're watching a recording. Did I say a bad word? You're all smiling at me. No? Okay, good. All right, I can never quite tell. Not everybody gets to grow up in a family where nobody swears. All right, here we go. 35 plus 273.15. Oh, it works best if you turn your calculator on first. Pro tip. That's why they pay me the big bucks. All right, that gives us 308.15 degrees Kelvin. All right, so that's our first temperature. Okay. 308.15. They also gave us our first pressure. That's 84 kilopascals. All right, how about our second temperature? How are we going to get that? What's our second temperature? Or do we have a second pressure? We're going to have a second one of them. There you go. That's right. It's good. Well, no, hold on, careful. It didn't say 230. It said it is heated an additional 230. See the word add in there? Literally means you're going to add it. So 308 plus 230 degrees. Now here's the thing. We don't have to add, we can add 273 to get the second temperature here. So we could just do 230 plus 273.15, and that would give us the second temperature, but we can also just add 230 degrees to this one. Okay, because they're the same scale, they're just shifted up or down. So plus 230. So our second temperature is going to be 538.15, which means that the thing we're solving for is our second pressure. Okay. So I really like to cross multiply to make these work. So that would be, anybody have questions before I start doing mathematics? No? So that would be 84 times 538. So let's do 84 times 538.15 is equal to, and we're going to cross multiply the other way, equal to 308.15 times x. All right. How do we get x by itself? Yeah, we can divide both sides by 308.15. That means the 308.15s cancel out, and we can start plugging it in. So here we go. We're going to go 84 times 538.15. Then we're going to divide by 308.15. And that means that x is going to be equal to 146 point, let's go 7, yeah. Are we done? Are we done? We are not done. We are not done. What did we miss? Units. No units, no points. KPA. Because we were solving for pressure, and that was the first unit we used was KPA, and we never change units when we're doing the two variable gas law problems. All right, I heard a couple people say I'm lost. Ask me questions. What do I need to explain?
Where did you get the 273.5?
Ah, good question. Where do we get the 273.15?
Kelvin.
Correct. So if you go over to page 66, the way to go between Celsius and Kelvin, if they give you Celsius, you add 273.15, and that gives you Kelvin. Good news, I will always give this to you on an assessment. That's not a thing you have to memorize.
Which page is this?
This is page 66.
Okay. See if I have it.
Here for you. All right, my dears. Shall we do another?
Why you gotta tell me, Dad?
All right, now I have already made a video that walks you through question number 5. Does somebody want to walk us through question number 5? We feeling it? Anybody? No? Wow, lots of hedge. No, okay, great. It would be my pleasure to walk you through number 5. Here we go. How should we start? Okay, let's figure out which variables we're using. P, V equals N, R, T is always the place we start. Let's fill in some of these. All right, it tells me pressure of 5.4 atmospheres. Do we have a volume in there? Okay, 120 liters. Are we good with atmospheres as a unit of measurement? Okay, so we're good on atmospheres. How about liters? Are we good with liters? Is that the correct units? If anybody's wondering how you figure that out, you go back to page 66 where all of the important things are and check what units you can actually use for this. Okay, so we've got 5.4 atmospheres times, let's see, ATM, and 120 liters, okay, is equal to, do we know what N is? What is it? No, that'd be a capital N would be nitrate. Okay, it's 4.0 moles. So I haven't really taught you what a mole is yet, so you can just put N if you like there, but it's moles. We'll learn more later. All right, next up is R. How are we going to figure out which number we should use for R?
We're using ATM.
Okay, so we're using ATMs as our pressure, so we're going to have to use the gas constant that works with ATMs. So come on over here to 66. Everybody take a look. Which one of those gas constants is what we use when we have ATMs? That's right. See how this one says liters times atmospheres? That means this is the right one. So 0.082. 0.082. And the units on that are ATMs times liters divided by moles times Kelvin. And that makes sense if you think about it as a constant, because that means it takes all the other variables into account. Finally, they are asking us, what is the temperature of the gas? That means that that is the thing we'll be solving for.
Oh, we have a lot.
All right? So we are recording right now. Here we go. We're on question 5 on page 73 if you want to join in. All right. So I'm going to rewrite this mathematics, and then we're going to solve that. So it is 5.4 times 120 is equal to 4 times 0.082 times x. X is our temperature. So good news. We're back to the part where this is basically middle school mathematics. 5.4 times 120 is 648. And 4 times 0.082 is 0.328. We've still got our x. Where do I go from there? Okay, we can divide both sides by 0.328. 0.328. Those will cancel out over here. 648 divided by 0.328 gives us x is equal to 1975.6. Are we done? No. Kelvin, that's right. 1975.6 degrees Kelvin is our answer. No units, no points. Just kidding. No units, less points. No work, no points. If all you gave me was 1975, no units and no work, you would not get any points at all. All right, if you cannot show me that you can do it, I cannot show you the points you deserve. All right, them's the rules. All right, my dears, we've got some good time left. Shall we continue? Now, you will notice at the bottom, is this answer exactly the same? No, probably I did some rounding when I made the answer key, or maybe I used 0.08 as the value instead of 0.082. In chemistry, we're not super concerned about getting the exact answer. If you're like 1% off, I would never worry. Okay? That's pretty normal in chemistry. All right. I'm kind of proud of this car problem. It's an intriguing problem. I enjoy it. So, shall we? Yes? Okay. So here we go. How do we start? Say it again? Find our variables. P, V equals N, R, T. All right, let's read through this. A specific car has an internal volume of 2,600 liters. So I'm going to write 2,600 liters over here, over by pressure. If the sun heats the car from a temperature of 20 degrees Celsius to a temperature of 55 degrees Celsius, okay, so we're going from 20 degrees Celsius to 55 degrees Celsius, what will the pressure... Oh wait, has an internal volume. I don't know why I wrote that over there. Okay, volume of 2,600 liters, temperature's changing. They want to know about the pressure. Interesting. So assume the pressure was initially 1 atm. That makes sense. If you open a car door, the pressure is going to equalize with the outside, and the pressure outside is always 1 atm. Okay. Do we know anything about the amount of gas? Not currently. All right. Folks, I know they said that the volume was 2,600 liters, but I have a question for you. Would you consider a car a rigid container?
I mean, no.
Can you pump a car up like a balloon? No. So if you can't pump a car up like a balloon, it counts as a rigid container. A rigid container is anything that doesn't expand or contract. Does that make sense? Okay, so if a car is a rigid container, we don't care about the volume because it's not going to change. Does that make sense to everybody? So we can cross out volume. We always cross out R. Okay, hey, it turns out this is just a pressure and temperature question. Everybody okay? All right, so here we go. Let's set this up. This is pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. All right. Pressure 1, 20 degrees Celsius. I'm sorry, that's... Hold on a second. Pressure 1 is going to be 1 atm. What about temperature 1? What's our initial temperature? 20 degrees Celsius. How do we feel about that? No, we would never use Celsius. That's right. It's Kelvin all the way. So, 20 plus 273.15. All right. And that's going to be equal to pressure number 2, which we don't know, so that's our X. And what's our final temperature?
328.15.
Ooh, how'd you get 328.15?
I added 273 plus 55.
Very nice. Added 273.15 plus 55. All right, my dears, can we cross multiply?
Yeah.
Can I show you a trick?
Yes.
This is back from AP Chemistry where you have to be able to do these questions unreasonably fast. If you've got two fractions set equal to one another, you can do the top over here times the bottom over here divided by whatever's left. Okay, it's always true. This times this divided by whatever number you've got left. So 1 times, oh wait, we can't do that because I don't have a fancy calculator. So 55.273.15. Nope. Try again. 55 plus 273.15 equals, all right, so we're going to do that times 1 atm divided by, what's 20 plus 2? So that's going to be 293.15. So divided by 293.15. Okay, X is going to be equal to 1.1. We're going to round to 2. Are we done?
No.
No. What do we need?
Units.
Units, so ATMs. There's our final answer. The pressure went up in a car. Yeah.
You're usually very good at math.
I don't know if there's such a thing. I think you can be good or bad at number sense, but I think math is just practice. Like,
Yeah.
I don't know if I'd say I'm very good at math. I'm very practiced at math. I took a lot of math, and when I went to college, I kept taking math. And because I kept taking science, I was doing a lot of math there. I'm really good at algebra. I've done a lot of algebra.
I'm sure.
Yeah, but it's really just practice. The more you do, the better you get. I almost failed algebra in 8th grade, so, you know, I wasn't...
Eighth grade.
Was it algebra then? Yeah, that was algebra. Yeah, I almost failed algebra 1 in 8th grade.
Wow.
Yeah. I took it in public school.
Yeah, it's normal in public school to take it a little sooner. It's honestly a mistake. One of the reasons I almost failed it was I couldn't hold the numbers in my head and like see them because I was just too young.
Yeah.
Yeah.
Makes sense.
Not everybody is, but I certainly was. All right, flipping it over. Wow, look at this. How many units of gas are in the car in the previous problem? What a cool question. You can literally figure out exactly how many molecules of gas are in the car.
This is rad.
Thank you. I'm excited too. All right. How should we start? How should we start? Same way we always start. PV equals nRT. PV equals nRT. All right. Now, if we look back at the old question, we can talk about our initial pressure and temperature or our later pressure and temperature. It really doesn't matter. Can we stick with initial so that we can use nice, neat numbers like 1? Yeah? No? No. Connor says absolutely not. We will be using the later numbers. No. Sorry, Connor. Overruled. Okay, here we go. So we're going to focus just on the initial. What was the initial pressure in this car?
1 atmosphere.
1 atmosphere. So we're going to do 1 ATM. What's the volume of this car?
Like 2,000 something. 2,600.
2,600 liters. Okay, is going to be equal to, we're trying to figure out how many moles of gas, so we're just going to put that there. Which R value should we use?
I'm not sure.
Well, let's go back to page 66. What units are we using for pressure? Atmospheres, ATMs.
So it would be the 0.08.
Right, and the way we know that is it says atmospheres over here, atmospheres right here. If we're using kilopascals, we would have to use the other one. All right, so here we go. 0.082, and the units on that are ATMs times liters divided by what? Oh, thank you. Wow, y'all, I really thought somebody was dying. All right. Atmospheres times liters divided by moles times Kelvin. All right, and then temperature. What's our initial temperature? It was 20 degrees Celsius plus 273.15, because we would literally never do a problem in Celsius. Ew, disgusting. How embarrassing. All right, for anybody just joining us, you can go to page 73. We're working on question number 7. That's okay. You can just watch, or you can go get it. All right, here we go. All right, my dears. Folks, at this point, this is just algebra. Would you like me to rewrite it for you so it looks like algebra?
Yes.
Okay. To rewrite it, you just ignore all the units. Look. Suddenly, okay, that part's hard. 293.15. I went ahead and added those together to get rid of the units. Now does it look like algebra? A little more? Okay. Hey, good news. We multiply these together. It's 2,600 on one side. Over here, we're going to do 0.0. Wait, hold on. What happened there? 0.082 times 293.15. All right, we've got 24.0383 times x. Can you solve that?
Yeah.
If you say no, I'm telling Miss Anderson. I'll snitch on you just like that. All right. I'm going to divide both sides by 24.0383. Divided by 0383. That's the joy of dyslexia, in case anyone was wondering. Okay. Those are going to cancel out. So here we go. 2,600 divided by 24.0383. Okay, x is equal to 108.16, and our units for that is mole. That is exactly how much gas is in that car, down to the atom, if we wanted to figure it out. All right. Isn't that wild that we can estimate something like that? All right, we have done a lot of practice problems. Who wants to walk us through question number 8? Surely someone in here. It's you?
Oh, Riley does.
Right? Rodimus does? All right, Rodimus, here we go. All right, Rodimus, we start every problem the exact same way. How do we start it?
Hands are sweaty. Hold on.
You got this, you got this.
Can you repeat the question?
Yes, we're doing number 8. You're thrilled, obviously. We start every question the same way. What do we do to start?
Well, we need to get the P and V.
PV equals nRT. All right, so let's read through this question. And every time you hear a pressure, a volume, an amount of substance, or a temperature, tell me and we'll write it down. Okay? All right. So you can just sort of scream when you hear one of these. Just like a quick, like, ah, something like that. Okay? Here we go. A helium weather balloon has a volume of 28,000. Oh, incredible. Volume. Wow, we found it. Okay, so our volume is 28,000 meters cubed. That's a gross unit. We don't do meters cubed. All right. Oh, wait, I said pressure. I lied. It was volume. Oh my gosh, I'm so embarrassed. All right.
It's okay.
It's okay. Thank you for your encouragement. All right.
Go to pressures.
When it is on the ground at an atmospheric pressure of one, no scream, seriously?
Wait, okay.
Hold on. I'll give you your line again. Ready? Okay, here we
You have to
go.
read the full thing.
28, the full thing. All right. A helium weather balloon has a volume of 28. Okay, we got volume of 28,000 meters cubed when it is on the ground at an atmospheric pressure. Okay, you tell me the variable. Thank you. All right. 102 kPa. I already took up the space where pressure should have been, so that's fine. I'm stealing some of the space up here. 102 kPa. All right, so we've got our pressure, we've got our volume. If the balloon rises to a height of 1,000 meters,
Oh, no.
is that one of our variables, height? No, I don't think so. All right, so no screams, just kind of, we could do just like a ugh. All right, so the balloon rises to a height of 1,000 meters, where the pressure is, oh, wow, great job, y'all. Wait, are you telling me that we have a before and after pressure?
That is weird.
Huh, a second pressure. So kPa, this must be pressure 1. This, 89.1 kPa, that must be pressure 2.
Yeah.
Okay, this is sounding like a problem we've done before. And then it wants to know what will be the new volume of this balloon. Ladies and gentlemen, did you hear anything about temperature? Me neither. Did you hear anything about the amount of gas? No, theoretically, if it's in a balloon, that's not changing. Those are closed. Okay? R is always constant. Hey, y'all, this looks like a pretty simple problem. Take a look at page 67. Which gas law should we use? What gas law do you want to use here?
Boy's law.
Look at Boyle's law. Boyle's law looks like he's there for us. All right, here we go. So that is going to be pressure 1 times volume 1 is equal to pressure 2 times volume 2. Shall we plug in our numbers?
Yes.
All right, Rodimus, walk me through it. Where am I plugging in these numbers?
Okay, well, you're going to plug in pressure for 102
Good.
kPa.
Okay, and I'm gonna leave out the. I'm gonna be crazy, and I'm gonna leave out the units right now.
Thank you.
Stay strong. It's gonna be okay. I know. Everybody, don't get crazy. Don't get crazy. Actually, that's a poor choice, but whatever. What's our volume 1?
Volume is 28,000.
Actually, it's not. It's 28,000 meters cubed. Now, here's the thing. We don't normally work in meters cubed. However, as long as it's meters cubed on this side, it will also be meters cubed on this side. If you're comfortable telling me the volume in meters cubed, that's fine.